Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 165 and 166, and we are discussing the Gibbs Phase Rule and its application. And last class we considered this second examples. We are considering number of examples. 12 examples we will be considering. So we are into the second example. This is actually FeO plus CO goes to Fe plus CO2, this reaction equilibrium, and we discussed 2 points that I want to mention here is this. Is this, that is well, this one, this actually I wanted to tell you that this is about this. Actually, we will be discussing today alternative stability diagram of the system APCO. But one point I want to mention about this, in the last class we actually constructed this stability diagram, and remember this, what I didn't mention here, T is constant, T is fixed. T is fixed. This diagram, recall, we call this I'm sorry, this line, we consider this line, okay, this line, this is Fe, this equilibrium 1, this one, this I mean equilibrium, this one, this is FeO equilibrium, and PCO is plotted against PCO2. The question that I want to raise myself is this degree of freedom is 2. Also, actually, I want to clarify this point. This is, since it is 2, but the line, forget about these two lines. This is about, actually, this is a P is PCO plus PCO2. P is PCO plus PCO2 is 1 atmosphere, and this is PCO plus PCO2 is 2 atmosphere. This line and this line, don't consider this. I focus on this line, this one, just this one, FeO equilibrium. So this one, this I actually showed that actually this has actually slope, yes, here. PCO is 1 minus PCO2. Now this is about these lines, okay, this is, but these lines actually it was shown here somewhere, yes, PCO versus PCO2 is actually a straight line, this straight line from these equations. PCO2 by PCO is constant, so PCO by PCO2 is constant. It is a straight line behavior. And what is the which straight line? This straight line. Okay, so just constant, start from this point. So Fe and FeO coexisting along this line, and above this line Fe is solid stable, below FeO solid stable. This is okay, no problem. Problem is that this equilibrium has 2 degrees of freedom, and we actually know, we want to actually understand this phase rule applications and the stability diagram in a number of ways, and to see that, make sure that they are consistent. So consistency, one thing I told you, remember that when degrees of freedom is 2, then it must be 2-dimensional representation. but a straight line is one dimension. So how you justify then these two? The answer to this question is this: it is a straight line, but this is straight line after we fix T. T is fixed, say 900 Kelvin. So then after that, it is a straight line. So 1 degree of freedom is already exercised. Then what? How many remains? 1 remains. That 1 is manifesting as a straight line. This is the justification. So you be careful when you are considering this one dimensional curve, but the degrees of freedom is 2. You should watch about this one, that whether this diagram is drawn after applying 1 degrees of freedom already, which has been done here. This I missed last class. Okay, that this is why it is a straight line, AP-APO curve. See here, it is actually, see these equations is given here. This is PCO, this is a T fixes KT, and PCO2 by PCO is constant. Since T fixes KT means KT is now a constant value. Since T is fixed at a fixed value, say 900 Kelvin, this gives a KT is a fixed value, and then PCO2 by PCO is a constant, or PCO by PCO2 is constant, and accordingly we got this line. So line, so why this happens? Okay, fixing T. Since we have fixed T, I have already mentioned here T and P. So T fixing T, this diagram we got. So this is actually this, and then actually I will draw another line, because this is for total P is how much? T fixing T and P, 2 degrees of freedom. The one is temperature, another is pressure. Pressure is actually, total pressure is fixed at 1 atmosphere, say. It can be 2 atmosphere, what I was shown is 2 atmosphere also. So one figure for 1 atmosphere, another figure for 2 atmosphere. So this is the plot of PCO versus PCO2, and this is actually obviously a negative slope, and these are 2 parallel lines. So now consider one of them, they intersect here. Then what it means? A point. This is the state. This is the state where this actually along this line, how many phases are there? Okay. So when you fix temperature is fixed here and pressure is fixed along this line, means 1 atmosphere. So what is the so what is this? What is the this state means? This state means AP-APO in equilibrium with CO-CO2. See, along this line, AP-APO is always in equilibrium with CO-CO2. So and say along this line, any points, any state, say here. Say this is the PCO, this is the PCO2. This is the PCO. Then if you fix pressure, if you don't fix pressure, then say the total pressure will be what here? This is the PCO2, this is the PCO for this state. For this state, this is the PCO2, this is the PCO. Again for this state, PCO to PCO. So total pressure changing. So if you fix this pressure, so system is not fully defined. This equilibrium is not fully defined unless 2 degrees of freedom are applied. So to fix this, which point means AP-APO is okay. AP along this line, AP-APO and APO are in equilibrium along with the gas composition. But what you cannot say from this, what is the total pressure? Because our requirement is that the system must be described in terms of temperature, pressure, and composition of each phase. So everything must be specified, then the state of the system is defined. So and for this purpose we have 2 degrees of freedom here, a number of freedom, and that is 2 here. So temperature, pressure, and it's clearly seen that yes, really correct. So when we fix temperature 1 and we get this line, but what is the purpose of this line, say for example? So why I drew this line? Is this line is not sufficient? This line. This line is not sufficient, AP-APO. Not sufficient because yes, This also gives the coexistence of APFO. I have written somewhere the coexistence of APFO along this line. Above AP alone, below APO alone, along with the gas composition always. Gas refer to the axis for the gas composition. Okay, here PCO, PCO2. So question is, suppose we actually consider, yes, along this line APO in equilibrium as this reaction suggests, and with the PCO, PCO2 which are varying along this line like this. This goes on, okay. Then what is the total pressure? PCO plus PCO2, so it changes. So we cannot specify the pressure, but our purpose is that to specify the state of the system in terms of temperature, pressure and composition fully defined. So that's why we have two degrees of freedom, so pressure must be specified. How? When you specify the pressure, say 1 atmosphere as I have shown here, which leads to this equation, PCO plus PCO2 is 1 atmosphere, so gives you PCO is 1 minus PCO2. This is plotted by this line, plotted, and this line is generated, this line. When it is 1, when it is 2, this line is generated. So suppose 1 we consider, so consider this line and this line, then see you get a point, intersection. This is the state of the equilibrium. What is equilibrium? AP, what is here? What does it mean? AP and APO, of course, in equilibrium with the gas composition at the total pressure of, what is this? This is 1 atmosphere. If you consider this point at a total pressure of what? 2 atmosphere, and so on. So this is purpose. So what I missed, or what I wanted to add today, that it is T is fixed. You must write, must mention T is fixed. Not only fixed, if possible, what temperature, when you want to quantitatively draw the lines, T is fixed at 900 Kelvin, 1000 Kelvin, okay, 1200 Kelvin, etc. So you might mention that. This should be actually the quantitative values. So this you mentioned, that means 1 degree of freedom is already applied. How many remains then? 1. And then if you draw this, then it will be a one-dimensional figure. And of course it is APFO. One-dimensional figure. Equation also I showed you here, it shows here. PCO2 by PCO is a constant, means straight line behavior. PCO versus PCO2. Okay, so this I wanted to mention, that although apparently contradiction. So that's a one dimension, but degrees of freedom is 2. No contradiction. 1 degree of freedom already applied, and the remaining degrees of freedom is manifested as a straight line. Thank you. So this part is over. Actually, I wanted to start with this. I am underlining this one, alternative diagram of this one. Instead of this, another diagram I will show you today, and for this purpose, so I should remove this. This is not required anymore. This is not required anymore. This is alternative diagram. I will draw it. So for this, let us. So since this is still in the second example. Second example we are still in the second example. I will continue with this one type of stability diagram I have shown. Also, by the way, don't look at this. This is for problem number 5. We are now in 2, second problem. And this is also, don't look at this. This is problem number 3b. Problem number 3. I'm sorry, example number 3. This is example number 5. So these figures don't, okay, look at them. Okay, consider second problem. So alternative diagram. What is this? You start with this. What is the KT? KT is what? 1. KT 1 is what? Okay, let me start with this. Start. KT1 is, you see, write this, you know already, here, you clearly see PCO2 by PC1, okay, already. PCO2 over PCO, Okay, only last name. And also you see here, actually I can write if you are interested, times once more, times activity of Fe, which is 1, and activity of FeO denominator, both are 1. So gives you PCO2 by PCO, okay, right? PCO2 by PCO, okay? Or this gives you what? Or PCO over PCO2 is 1 by kT, equilibrium constant at temperature kT1. Or just little bit manipulate, or PCO over PCO plus PCO2 is 1 by kT1 plus 1. Better rewrite this way, 1 by 1 plus kT1. Okay, this is known as what? What is this? PCO over, means NCO over NCO plus NCO2. Same. Partial pressure ratio, partial pressure PCO over PCO plus PCO2 is NCO by NCO plus NCO2. What does it mean? The mole fraction of CO, or in the gas mixture CO-CO2, or XCO is 1 by 1 plus kT1, okay. Also continue this, continue where you continue, okay. So I only maintain this. This diagram, this is the system, Fe, FeO, CO, CO2. This is the actually experimental system. Simple diagram. I am removing this. This part is already over. So removing this. This is not required anymore. This I removing this. Remember, this is our system, reaction system, and this is a sketch. This is the reaction system we are discussing. For this, we are trying to draw an alternative stability diagram. One I have already shown, and this is the one, and this is the system sketch. And so you remove this part. This part is okay. Wait a bit. So we actually now will find the equations which will plot to have the alternative diagram, stability diagram. So this is our job. Okay. So these are actually the initial things. I didn't want to disturb this. This is the basic things, that is number of degrees of freedom is S2 actually here is a C minus 2. C is given here as 3. P is number of phases. All these are basic things, basic consideration from which we get the degrees of freedom as 2. This I am not disturbing. This is our study. Reaction understudy or equilibrium understudy, you may call it. It is a reaction equilibrium, reaction system. So this system we are discussing. So alternative diagram for this. Start XCO is 1 plus 1 kT. Or so what? I am giving a star mark here, and let's start from here. That will be helpful. Start here. So what is percentage CO is what? This percentage means mole percent. This is mole fraction. mole percent is 100 times 100 times this 1. What is the KT is actually, you remember this, it is e to the power delta G0. Why? Recall delta G0 is minus R3 ln K. Use this, okay? Or further is another line, 100 over 1 plus, what is the delta G0 is in the which form it comes? A plus BT, A plus BT over RT. Delta G0 is A plus BT. Right here, delta G0 is written in the form two-term expression. A plus BT is what? Is actually A is what? Recall A is delta H0 and B is minus delta S0. You know this. This is A U0. These are known from data book. Known from data book. So A and B are known just from data book. Always say A plus BT. I am written in this, or right, or percentage CO. So AB is known. Okay. I made a mistake. So let us see, check this from here. K is e to the power minus, yes, delta G0. K is e to the power minus. Correct. It is correct. Delta e to the power minus delta G0 over RT, and delta G0 is A plus BT, or A is delta H0 and B is minus delta H0. So this is percentage CO versus T relation. This is the percentage CO versus T relation. So you can plot this. That will be the stability diagram. So let us plot here. I am plotting here. Percentage CO, percentage CO versus T. What type of relation? Tell me what type of relation this one. Previously you got this straight line relations, PCO versus PCO2 when you plotted the previous figure. This will be which figure? This is figure 2A, 2B already I have removed. This is figure 2C. Percentage CO versus T plot. You may call this figure 2C. 2C. Okay, this is 2A, 2B. I have removed 2C. Okay, this is now what type of relation? This is the percentage versus T relation, which is what type of relation? Linear? No, it is non-linear. Okay, so e to the power, which is non-linear. It's non-linear. So let us look at how it will look like. This is, and you see what is this? Is along this curve which exists, the AP, FO exists, and above this, when CO increases, AP will be stable. So AP above, below FO. Along this curve, AP, FO equilibrium. Okay. So AP solid, FO solid. You can write this. Let's extend this. Ap solid, APO solid. Along the line, APO coexist. Above AP alone, below APO, and then each case you have always percentage CO in CO-CO2 gas mixture. In CO-CO2 mixture. In CO-CO2 gas mixture percentage CO. Okay. So this is the okay. Now question is, now again you see what is this? Okay, very good. Okay. Very good. Okay. So CO-CO2 mixture. In CO-CO2 mixture you may write. In CO-CO2 mixture. Okay. So this part is now how to, can you explain? Again you have a curve. Again you have a curve means one dimension, but these are the 2 degrees of freedom. Again the same problem comes back. So you see what is the meaning of this? What does this figure, this stability diagram? Oh, it is actually alternative stability diagram for the system. So it is better than right. Anyway, it is alternative stability diagram. Alternative, which is very popular. Alternative stability diagram for the system APCO. Okay. For the system APCO. For the system APCO. This is figure, mention also that figure 2C. Figure 2C. Okay. So again this problem, see what does it mean? One dimension means you fix one. Suppose you fix temperature. This temperature is just arbitrarily. Then you go up. This temperature is this point, and then see what y-axis reads this. If you have this temperature fixed, okay. If temperature is fixed, you fix temperature, then percentage CO is fixed, 1 degree of freedom. Conversely, you fix percentage CO, this temperature will be fixed here. So one choice. But 2 choices are there, degrees of freedom. See, even you fix a temperature, you know percentage CO. Do you know everything about the system? Which you are supposed to know. Which you supposed to state, to define, which is supposed to submit or furnish to define the state of the system. Do you? No, really? You know temperature, very good. You know percentage CO, admitted. But still, what is missing? Suppose I ask you, mole percent CO, you know mole fraction. You might say, oh, mole fraction CO means I know the composition of the gas. Very good, allowed. Agreed? You know the composition of the gas, you know the temperature. Then do you know the pressure? Pressure of the system? You don't know. So that means this is, you need to, this looks like, okay, this here, 2 degrees of freedom have not been yet exercised. One you have exercised, you know this. So you don't know the pressure. For example, another way I am telling you. Suppose you tell me you know the mole percent CO. You fix a temperature, mole percent. You can fix this also. So why with this? Change here. Then what it will be? Oh, sorry. change here, draw this. Here, and then here. Fix this temperature, this is the CO, you know. So XCO, mole percent in mole fraction, you know. Composition, mole fraction, you know. Do you know partial pressure of CO? If I ask PCO, you must know everything by defining this temperature. So actually you are entitled for 2, and if you don't do this, system is not defined. As I said, that the both of all degrees of freedom must be specified, must be utilized, must be specified to define the state of the system at equilibrium. What does it mean? Temperature, pressure, and composition of all phases, or each phase. Happy? So you cannot answer. PCO you cannot answer. Or I say, ask you, what is the total pressure of the system? You don't know. So even so, this curve shows a stability diagram. Pressure is not mentioned. Pressure is to be specified separately. Okay. So then the 2 degrees of freedom will be utilized. Not only that, the system, your desired goal system will be defined at equilibrium completely. So this, another thing note, this is actually a pressure independent curve. This is another very interesting pressure independent curve. It is better you write that pressure. What does it mean? Pressure, which is P, total pressure independent curve. This equilibrium. This about something like that. I'm going to write this. Okay. So note, importantly, some comments I am actually now giving you. Okay, making percentage CO versus T plot is pressure independent. Is pressure independent, as can be seen from let us give a name to this equation here. What equation? So we have written actually, it is 1, that is 2, 3, etc. Equation 3 say, as equation 3. Call this equation 3. You follow last class, it is equation 3, okay, as can be seen from equation 3. Also from reaction 1, also from reaction 1. Reaction 1 is what? This one, reaction 1. So why it is from 3? Why it is pressure independent? Where is the pressure term? Where is the pressure term here? In equation 3. So pressure independent. It is pressure independent. Means does not matter whether it is 1 atmosphere or 2 atmosphere or 3 atmosphere, same curve. Then the question comes, so why, if it is independent, why should we mention? But you have to specify a pressure. This curve will not change, but you don't know the pressure of the system. So that's why pressure is to be specified 2 degrees of freedom. Pressure, because you don't know the pressure of the system. System is not fully defined, completely defined. That is another issue. That you have to define the state of the system, you must Note the pressure, specify the pressure, give the pressure. But at the same time, it is true, it is also true, it is equally true, it is to be admitted that this curve will not be modified by change in pressure, will not change with the change in pressure. For 1 atmosphere, this line, 2 atmosphere, same line, 3 atmosphere. This is the message, okay? But why it is pressure? So pressure independent, that's why actually you have to separately give the pressure value. The pressure is, system pressure is say 2.5 atmosphere, or say 3 atmosphere, or 4 atmosphere, or 1 atmosphere, specify. So, but is the pressure independent from one this? Another thing, also from reaction 1 also, can you tell me? Reaction 1 is where? Here. Is it pressure independent? Why? Which reaction is pressure independent? Where the number of moles of gas moles are same in on the reactant side and the product side. So 1 mole CO and 1 mole CO2. So pressure will not affect this. Okay. So this is the reason. So also from reaction 1, you can write this. Reaction 1, since the same number of moles of reactant and product gases what are there? Here 1 mole each. 1 mole each of CO and CO2. Remember, pressure about gas species. So gas moles, if they are same, now when it will be pressure dependent? When it will be pressure dependent? When the number of moles are different. Very good example that I will take up the next one. CO2 plus C is 2 CO. This system. 1 CO2 left hand side, 2 CO right hand side. That is pressure dependent. This is pressure independent. Okay. So very good. 1 mole each of CO and CO2. So reactant products are same, are involved. So also from reaction 1, since the same number of moles of reactant and product gases are involved, reaction 1 is independent of pressure. Reaction 1 is equilibrium 1 is independent of pressure. Pressure. So two different ways you see. From this equation also you see that this plot is pressure independent, and also from this reaction itself it clear that it is pressure independent. Okay, and this is the plot. This is the alternative stability diagram. This is a stability diagram. Okay, why stable? This is here AP stable, above the curve AP stable, below the curve APO stable. Along the curve APO coexist, both stable. Stable means equilibrium. Here AP stable means AP is the equilibrium phase. AP solid is the equilibrium phase. Below AP solid, APO solid is the equilibrium phase. Along with the gas composition here. So AP and gas. Here APO and the gas, and along AP plus APO plus gas. So three phases. Here, see, three phases. So this is actually, remember this point is clear. Even so double star. So like double star, and I have to remove something. Okay, double star here. You may not look at it. Here, double star. It is better I give here so that double star. Okay, it is better I remove. These are not required. Oh, if is this line, I should not. Achha, I am removing this. Let me remove, because actually I have to remove few lines. I have to remove few lines. Yeah. So since we are going to conclude this second example, so just this space will be good enough. Huh? So even so, start. Note this. Even so, I have already mentioned what I am saying. Even so, it is pressure independent, admitted, but still you have to mention, specify the pressure, otherwise state of the system at equilibrium will not be defined at equilibrium unless we know the pressure. So even so, and that is also required by the degrees of freedom. F is 2. I have removed this. F is 2. So temperature, pressure. Even so, pressure P as the second degree of freedom. As the second degrees of freedom, which I will abbreviate this way, DOF. Degrees next, now onward, DOF. Second degrees of freedom must be specified. To completely define the system. To completely define the system in terms of, you know what, always I repeat, I'm repeating in terms of, you know, let us remove this line since these are all used up in this diagram, all used up in terms of temperature, pressure and composition of each phase. At equilibrium. At equilibrium. So this is about pressure. If a role of pressure, you must be very careful to seemingly opposite roles. Means in one case we see pressure has no role. So why you consider pressure? You may argue. No, you have to. Even though this curve, this equilibrium curve is not dependent on pressure, but unless you specify the pressure, system is not defined. That is the answer. And why it is not in? Why, sir, you are saying it is independent of pressure? The percentage CO will not change at any temperature. Percentage CO will not change if we change the pressure. No, it will not change. Will be independent of the value of the pressure. At any given temperature, percentage CO will be independent of the value of the pressure. So that is independent, and that comes from the reaction. Same number of moles. Very easy to follow. This was discussed previously. So lastly, you have to follow. So note, extra additional note. This I say note. This is a different thing. This is again conceptual clarity. That what I tell, 2 degrees of freedom. What I chose Tp, what I want, but there are other variables we see. For example, mole fraction can be, percentage CO can be, mole fraction can be, partial pressure can be. This, remember, always I insist that how many degrees of freedom is the main concern. How many? Which are they is secondary, because that is actually matter of choice. How many? 2 is important. Who are they? Which are they? What are they? Not necessarily Tp. It can be T-PCO. It can be P-PCO. Mutually independent. They must be mutually independent. Like this. PCO, PCO2. 2. Or XCO. So this I want to mention. So this is conceptual clarity. Okay. Any. In principle, F2 can be exercised by independently choosing any two out of any two out of the variables. What are this? Variables, what is this? For example, yes, temperature, yes, pressure, yes, PCO, yes, PCO2, or any other modifications, such as PCO ratio as ratio. This percentage CO can be, this XCO, mole fraction CO can be PCO by PCO2, PCO by PCO plus PCO2 is XCO. So PCO by PCO2, PCO by PCO plus PCO2, which is XCO, is possible. PCO by PCO2 or XCO, I am writing here, etc. So note this important, that there can be other choices also. But obviously we tend to consider temperature and pressure as very convenient degrees of freedom. Convenient, but not compulsion. Theoretically no compulsion. Convenient. Okay, this is draw a line here, and this concludes example 2. Second example is over. Let us take the third example. So this is now time. Actually, we example 3. So remove this. Example 3 will deal with again carbon and oxygen system, which may look simple system, but this diagram is used, alternative is used. So this is for figure 5, that is okay. This is far away. This is example 5. Way later, this one 5, not now, but this diagram, if possible today we'll cover this, but next we'll take up the third problem. This diagram is about this third problem. So remove this. So now it looks good. Now we can keep writing here. Yes, let's start this. Okay, 3. This is 3 means example 3. Example 3. What is again the reaction system or reaction equilibrium? CO2 gas plus carbon solid is 2 CO gas. So if you ask me to draw a figure, sketch for this system, easy, very simple. Again, this is the pressure P, total pressure of the system. This is carbon solid, this single condensed phase, and this is CO-CO2 gas mixture. Gas. So clearly see 2 phases are there, and this is your temperature T under equilibrium. Always impress this upon yourself, your mind, never forget. Phase rule applies at equilibrium, and what else? Okay, this is okay. If you figure 3A, and this will be your 3, where it is 3B here, 3. Let us give a fencing here, just in case. Okay, this is give a fencing here. Okay, this will be much later, but this is currently coming. But start. What is the starting point? Write the phase rule. F is C minus P plus 2. So you will write C is what? Number of components This number of components is what? Number of, okay, you go by this number of elements. Elements is what? Who are there? Two here. Who are there? C and O. Carbon oxygen system. Okay. C, or alternatively, C is what? Number of species minus number of independent reaction equilibrium. Number of reaction equilibrium. Equilibria. Okay. What I am going to ask a time. No?
55 minutes 52 seconds done.
55 minutes means 1 hour.
1 hour. 1 hour still left. 1 hour 5 minutes left.
1 hour 5 minutes left. Oh. It's okay. Thank you. Number of species minus number of independent reaction equilibrium. I have already mentioned this. Reaction equilibrium. What is this? How many species are there? 1, 2, 3. 1, 2, 3. Okay. So 3 minus how many reaction? 1 reaction. The reaction that is written is 2. In agreement, same. What are the species? Species is what? 3 species. How will you write this? 3 species. Species 3. Species 3. Who are they? Right? CO2, carbon, CO. 3 species. Now reactions. So you are happy. C is okay. From both definitions, same value. So you are satisfied. P is what? Number of phases. How many? Now 2 here. One solid phase, one gas phase. One solid. What is that? Carbon. One gas phase containing CO-CO2. So put it back here. C minus P plus 2. C is what? 2. P is how many? 2 plus 2. So 2. 2 degrees of freedom. What are they? As I have told you, although we can argue, we can theoretically consider any values, any variables. Partial pressure, mole fraction, okay, temperature, pressure. So temperature, pressure we may consider conveniently. So Tp, equations that actually will be, resulting equation will be simpler to solve. Anyway, we can consider temperature, pressure, or we can, if necessary, we can change this also. Tp is okay. Now fixing T demonstration. You have to demonstrate this. What you will demonstrate? Demonstrate that by fixing F number of variables, the state of the system can be fully defined in terms of temperature, pressure, and composition of each phase. This is the demonstration. Thus, finding the degrees of freedom is not a big deal. Demonstrate how by fixing these 2 variables, the state of the system is fully defined. Demonstration. Fixing T. Fixes what you know? KT. So give it an equation name, perhaps CO2 plus C is 2C. Yes. This is always very important. Give a number to the equation. This equation number 1. It gives KT. Fixes KT is KT1. So only one reaction. So KT is what? Fixes KT. It fixes KT. KT is what? KT means I know KT. Since I have fixed temperature, so I know KT. KT is what? Write this. PCO square over PCO2, activity of carbon under equilibrium. Activity of carbon, carbon is solid, pure state, standard state, so 1. So it is PCO square by PCO2. PCO2, okay? You don't, okay? Equilibrium implied here, so I have already written one, so call it equation 2. And another is fixing pressure, total pressure actually. P is the total pressure, otherwise I actually call these other pressures partial pressures. Pressure of CO is partial pressure. Fixing total pressure P is gives you what? P is fixed, so is nothing but PCO plus PCO2 partial pressures sum. So P is known, so P is PCO plus PCO2. Call this equation 3. So solve equations 2 and 3 for PCO and PCO2. अच्छा, solving equation 3 gives what? 2 unknown, 2 equations. Always this. 2 unknown, PCO and PCO2, and 2 equations. Gives PCO is known, PCO2 is known, okay? PCO is known and PCO2 is known, okay? What is this? That means from which here you get, this gives you XCO is what? PCO by P, total pressure, is known. Or percentage CO is what? Mole percent CO, mole or simply percent CO is what? XCO times 100. So you can get this, okay? Is known. That is also known. Okay, sorry. And similarly, XCO2 is what? PCO2 by P is known, and mole percent CO2 is what? XCO2 times 100 is known, okay? So these are the known that you already see. And what is this is about the gas compositions are known, okay, in terms of mole percent. So gas compositions are fully known. Also solid, another the solid is pure carbon solid. So what is the XC? Mole fraction wise, pure, since pure 1, activity is 1, mole fraction is 1, all these things. So what you have demonstrated that composition of all phases known and temperature, pressure already are known from degrees of freedom that you have arbitrarily chosen, okay? Independently you have chosen. So you can write this. You are now by fixing the F is, what is this? F is 2, F number of variables, F variables. The system is fully defined. In terms of temperature, pressure, and composition of each phase. Each phase, gas phase and solid phase, 2 phases are there, compositions all known. Say mole fractions you are interested. So compositions are known, and composition of each phase at equilibrium. You write at equilibrium. You will write here the phase at equilibrium. This I will repeat always at the end. So by fixing that demonstration is complete now. Okay. So this is over. Then is stability diagram. We'll take up construction of, I repeat, the construction of stability diagram, how to construct that lesson will be taken up formally later for a more complicated system. This is a very simple system. So we are just touching upon this stability diagram because stability diagram and Gibbs phase rule, degrees of freedom are interrelated, intertwined. So good idea to understand this Gibbs phase rule more completely, more satisfactorily with the help of the stability diagram. Okay. And stability diagram is what will be this. Okay. This is the diagram already. This is this one. Figure 3b. This is the stability. I have written here. I have not written percentage CO. See, you have got this percentage CO here. Mole percent CO is known. That is plotted against temperature. Let me explain this plot. Then I will give you actually what I will tell you this about the stability diagram. This I will take up. Is how I have drawn this. This is the stability diagram for the system. This reaction system, or we may call it CO system stability diagram. See, there are two curves you are seeing. First of all, go slowly. Percentage CO versus T plot. I have written here percentage CO versus T plot at equilibrium, obviously. Actually, every time I am saying at equilibrium, why? Because where you have used the equilibrium. See here, equilibrium constant you have used. That gives an equation, and this equation helps you find the unknowns. So at equilibrium, so this is equilibrium diagram. Stability diagram is an equilibrium diagram. Okay, these all are equilibrium diagram I am drawing. Okay, so follow me. Percentage CO versus T plot at equilibrium for the system CO, two component system. Achha, this is you just follow one. This curve for 1 atmosphere total pressure, and the second curve is for 10 atmosphere total pressure P. Okay, one by one. If you understand one, you understand the other. So here, what is this? How this is because you already see, you know yourself for a given temperature you have fixed percentage CO is known. So you are taking number of temperatures and number of corresponding COs, percentage COs, and then you are connecting them by smooth curve, and this will be generated. Drawing, no problem. So several letters. Now what I want to tell you here. So yes, this is 0% and 100% CO, and these temperatures are Kelvin. This is 673 means roughly 400 degrees centigrade, and this is 1273 means 1000 degrees centigrade, and this is actually special value 948 Kelvin. This why this is special. Achha, follow this curve. Forget about this curve. This curve name, the first curve name A, B, C. A, B, C, and next one D, E, F. Okay, these I will discuss. Okay, this B prime, B1, B prime. This I will later on I will discuss this. Okay, B, A, B, C. And what is this? This is the temperature 948 Kelvin, which is actually an intermediate temperature between 673 and 1273. It has actually special value because if you consider the 1 atmosphere curve, this corresponds to 50% CO. So one thing I tell you, just consider 1 atmosphere. Under 1 atmospheric pressure or in general, percentage CO is about 100% when the temperature is 1273 Kelvin. Follow this curve. And the opposite, when it is 673 Kelvin, means 400 degrees centigrade, percentage CO is almost zero. 100% percentage zero in the CO-CO2 mixture. Percentage CO 0 means percentage CO2 is 100, and percentage CO 100 means percentage CO2 is 0. So, and this is what carbon CO2 C is 2 CO, this curve, this equilibrium curve. This we speak of carbon saturated curve, because activity of carbon is 1, solid, pure solid is present in the system under equilibrium. So activity of carbon is 1, and that we call carbon saturated. Very common phrase, carbon saturated system. So for carbon saturated system, so what you understand, that at high temperature, say 1000 degrees centigrade, 1273 Kelvin, it is this carbon and oxygen system. If you have oxygen, then this will burn to produce, this will react to produce CO-CO2 mixture. In the mixture, oxygen will be negligible finally, but CO-CO2 mixture, it is predominantly why? It is essentially CO at high temperature. High temperature in carbon saturated CO-CO2 mixture, it is 100% CO. It cannot be 100%, 99.9% say, and between close to 100%. Essentially CO. Similarly, at low temperature, as low as 673 Kelvin, it is 100%. Yes, 100% CO2 means 0% CO. Essentially, this knowledge you should know that. So if you burn oxygen or oxygen say in carbon at high temperature, what is the product? What will be your answer? What will be your answer? You will say it is CO, sir. CO gas. At high temperature like 1000 degrees beyond. And if it is 400 degrees centigrade or below, then what is the product? It is essentially this CO2. Then what is the gas composition between these two temperatures, namely 948 Kelvin, which is actually 675 degrees centigrade. The answer is this is known actually. The answer is it will be go up here. 50% CO, 50% CO2, 50-50. This is like this, okay? Or similarly, between this and this, it will be more than 50. Between these two temperatures, more than 50% CO, and balance is CO2, etc. So this part. And what is this? This curve is drawn for 1 atmosphere, the first one, ABC, when total pressure is 1. It's a total pressure, fixing pressure, total pressure is 1. Then you generate this curve. If the total pressure is fixed as 10 atmosphere, then you generate this curve. The same procedure. Otherwise, same. Okay. The another question is here actually I tell you what I will tell you. Okay. Yes. This is what I have labeled here. This curve is what I have written: carbon saturated CO-CO2 gas mixture. Carbon saturated, as I told you. Carbon saturated CO-CO2 gas mixture. In bracket, what I have written, carbon saturated means activity of carbon is 1. Clearly you see carbon solid, activity of carbon is 1. This curve, carbon is 1. I should write here. Sorry, is 1. Activity of carbon is 1. Is 1. Is 1. You know this. This is what these two things that I cannot explain now. This is written here: unstable gas composition. See, there is actually there is some okay, hatch lines. Okay, so these actually have been because above this, no, consider only 1 atmosphere curve. Don't worry about 10 atmosphere. This curve above this, it is not possible to produce a gas. Suppose you want to produce a gas above this at this temperature 948, no, you cannot, because this is unstable gas composition. Sooting will means carbon will be deposited and the gas composition will fall back onto this curve 948. Follow this. I will explain. Don't worry. I explain means okay. I'll clearly write this out. Okay, and this one, this is what this gas. Okay, this I will tell you here. Okay, here activity of carbon I have written somewhere. I have not written. I have written here. Sooting activity of carbon greater than 1. This actually I am showing telling. Here I have written carbon unsaturated gas activity of carbon less than 1. Below this curve, follow 1 atmosphere line only. Below this activity of carbon 1 atmosphere total pressure. Below activity of carbon is less than 1. Above activity of carbon is greater than 1. And on the curve activity of carbon is 1. Okay, I have said here activity carbon is 1. Carbon saturated. This curve on the curve. When it is greater than 1, then it cannot be possible. So it will try to get back to activity of carbon is 1. This is unstable gas. This I will help you. I will explain you with the help of the phase rule. So you will learn. You will always learn command mode. This curve, which is otherwise may be difficult, which is otherwise difficult, with the help of the phase rule. You will understand this. That's why I have actually brought into the brought the stability diagram into the picture here, into the discussion here. Okay, this what else I will have to keep like this. Okay, very good. This is okay. Thank you. So start. I'll keep explaining. Yes, the curve ABC. Curve ABC, which represents the equilibrium of reaction 1. Reaction I am writing reaction 1 short. Only one reaction 1. Reaction 1 is obtained by plotting the percentage CO versus T with the total pressure being what is the information about total pressure? This here you will make a contrast. This curve ABC, is it pressure dependent or independent? Answer is it is pressure dependent. That's why it changes. It changes to this curve DF as pressure increased. Or similarly, it would change if the pressure is decreased to say 0.1 atmosphere. So this will be another curve like this. So pressure dependent. Why dependent? Two ways. Pressure dependent. See, the equation will bring actually the pressure. The relationship percentage CO versus T relation will actually have involved pressure. Also from where? From the reaction itself. 1 mole gas left hand side, reactant side, 2 moles CO, 1 mole CO2, 2 moles CO, so moles difference. So pressure will affect the equilibrium. So that's percentage CO or percentage CO2 change actually. So it is. So unlike the last case, last examples, FO equilibrium was pressure independent, but this is pressure dependent. Clearly, that's why I have drawn two figures to show the effect of the pressure as well as other discussion, cover other discussion. Percentage CO versus T, with the total pressure being what value? Tell me. 1 atmosphere, as I will say. See, it is written here clearly. Clearly see. The P is 1 atmosphere. Say, I have said say actually. And this is P is 10 atmosphere. Say, okay. Being chosen, degrees of freedom, chosen as 1 atmosphere. The corresponding curve for is 10 atmosphere. Is 10 atmosphere is shown alongside which curve? Curve D E F. This is A B C. D E F curve okay, curve D E F. The curve shifts to the right with increase in pressure. Increasing pressure in compliance with the effect of pressure on equilibrium 1. Reaction 1 means equilibrium 1. On equilibrium 1 means equilibrium of reaction 1. Okay, on equilibrium 1. How it is? It shifts to the right. You clearly see? Shifts to the right. Okay. So what you see shifts this to this. What is the result? Clearly say fix the temperature, then you will understand easily. So consider 948. What is the composition for 1 atmosphere curve? Now B. B is what? 50%. CO. For the same temperature, what is the composition? For the same temperature, what is the composition? Tell me. See, B1. B1 for the 10 atmosphere curve. B1. B1 means it is a lower, since it is right, actually it will be lower CO. So with increasing pressure, lower CO. Let us see. If we increase the pressure, equilibrium moves towards which side? To a fewer moles of gas. So here 1, 2. So to the CO2 side. If you increase the pressure, CO2 percentage will be greater or CO will be lower. This is the picture. So, and that's why it shifts to the right. Okay, 10 atmosphere. Similarly, you can still increase 20 atmosphere. It will be further to the right. And to the left, it will be when it is less than 1 atmosphere, like say 0.1 atmosphere. So this is actually, so further explanation to this is what? Effect of pressure is this. As P increases, explain. As P increases, right, equilibrium shifts to the side containing fewer moles of gas that is towards CO2 side, that is towards fewer 2 against 1, that is towards CO2 side. 2 moles of CO, right here, 2 moles of CO on the right hand side, 2 moles CO on the right hand side, versus 1 mole CO2, 1 mole CO2 on the left hand side. Okay. This means at a given temperature, say it is, for example, 948. 948 K, say you can choose another temperature, any other temperature, 960, 1000 Kelvin, say 948 K, percentage CO decreases. That is percentage CO2, increases. From where to where? So this temperature 948 is, so this one dotted lines. B 1 atmosphere point comes down to B1, to lower CO percent or greater CO2, increases from B to B1, from B to B1. As P increases, from 1 atmosphere curve to 10 atmosphere curve, total pressure. As P increases from 1 atmosphere to 1 to 10 atmosphere. 10 atmosphere. Now I will take up an extra question. This is okay, discussed here. Extra question that will actually trigger many issues, that will bring in many issues. If you violate the phase rule, 2 degrees of freedom. If you use 3 degrees of freedom, this I said in the definition of the degrees of freedom. What I said, if you overdo the degrees of freedom, exceed the degrees of freedom, then what will happen? Phase elimination will take place. This I said. Today we'll discuss this part. Okay. So this is actually, let us start. Additional question. This is important discussion. Additional question. In the light of the curve,
One hour, 31 minutes, 40 seconds.
31.
Half an hour still left. 29 minutes left.
Okay. Additional questions in the light of the curve ABC. Curve ABC. Question. Additional question. What is the question? What is the question? What happens? Acha. What does it mean? Only concentrate on the 1 atmosphere curve. Forget about 10 atmosphere curve. The second one. Don't worry. Here, some question will be coming. Just one. P is 1 atmosphere. A, B, C. Concentrate here. I will exceed the degrees of freedom. Violate Gibbs phase rule. Then what will happen? Will this equilibrium be intact? What I answered previously, as I told you, that phase elimination. See, here some surprising thing will occur. Yes, phase elimination will occur. In one case, you third degree of freedom, two different ways will do this. One is I'll explain this. So some interesting thing will happen. But remember, what is the normal thing? Normal expectation that phase elimination will take place. Let us see. And a new equilibrium will be. Elimination takes place doesn't mean okay, you don't have any equilibrium. A new equilibrium having fewer phases. If it were two previously, now it will be 1. This. About this I will discuss. What happens if this is the question. What happens if the degrees of freedom is violated or exceeded? Exceeds, if the degrees of freedom exceed two, what are they? Temperature, pressure. Okay, this is a question. What happens? Question mark. Question mark. Okay. So the answer, let us what happens? Suppose Answer to this question. Suppose T is chosen 2 degrees of freedom. 2 we apply, then violating the third will apply. Suppose T is chosen means freedom, freely chosen, independently chosen. Suppose T is chosen as 948 Kelvin and P as 1 atmosphere. P as 1 atmosphere means this is referring to the curve ABC, not DEF, that is 10 atmosphere. So concentrate on the curve ABC, as I have said, only ABC, in the light of the curve ABC, discussing this current discussion. And P has 1 atmosphere. Okay? So the mole percent CO mole percent CO, or simply percent CO, you may call this mole percent CO under this condition is automatically fixed at 50%. At 50, mole percent CO is fixed at 50%. What is this point? Follow this. Follow. Here 948. Now 1 atmosphere means this curve. So go up. This is what B, point B. What this does it correspond to? 50%. So 50, fixed at 50. At 50 means 50%. What is this? Suggest point B or state B. Point means state. Point B. Point B. Now, so far so good. This area you see composition. Now you exercise the third degree of freedom, which you are not allowed according to the Gibbs Phase Rule. So let us see. Now if a third degrees of freedom third degree of freedom is applied, introduced in violation of the phase rule, a phase is to be eliminated. A phase is to be eliminated. Is to be eliminated. এখন হবে না, ক্লাস নিচ্ছি, ভিডিও ক্লাস নিচ্ছি। This is eliminated. Sorry for the interruption. This happens when percentage CO is arbitrarily decreased from B to where? B, see here. You have seen B dash, B decrease from B to B dash. Violating. Temperature 1 degree of freedom, pressure 1 atmosphere, 2nd degree of freedom, and still I want to have them in equilibrium with mole percent CO, which is automatically fixed as 50, violating that point, decreasing that from that 50 means B, point B to B prime. If I try to do this, then will this equilibrium be intact? No, we know the answer, phase elimination, so we'll discuss that. Arbitrary decrease from B to B dash, the carbon solid will be eliminated. This leads to phase elimination. So here what happens at B dash, you know what I have written here? This is also CO-CO2. CO-CO2 is there. Carbon unsaturated means carbon is no longer present. Activity of carbon is less than 1. That's why it is absent. It is missing. So this gas will be produced, but carbon is not there. What will happen? So equilibrium is there. You change this percentage CO decreases, then continuously the reaction will, from the equilibrium it will decrease. This equilibrium will move towards the right continuously until it eats up the carbon, consumes carbon and removes from the system. So it will give you this, actually the desired composition. So repeat, equilibrium is there with certain CO or CO2 at certain temperature, pressure. So that is 50% CO, but you have changed to a lower value, say 30%, then but that is not supported by the equilibrium. So what will happen? You try to reach that one, reach this equilibrium. Okay, that is okay. So as CO has decreased, so the reaction will, since equilibrium is disturbed, so reaction will move in this direction, forward direction, and consuming carbon until it is removed, fully removed. So and eliminated, fully eliminated. So what will be this has happened here, B2, B1. Okay, so so remember percentage CO. When you are doing this, you might say That's if it moves to this direction, then CO is increasing again. You have decreased and increased. No, sustained. It means you have sustained this. You sustain this CO percentage at this lower value of B prime, then continuously, again you have said, suppose it regains the equilibrium, then again you are decreasing to B prime, again moving. So all the time it is moving, and carbon is gradually being depleted, and time will come when carbon will be fully removed, and then actually this equilibrium given by the B prime will be available in the system. That is also an equilibrium. So this is an equilibrium state, B prime, but with the elimination of carbon solid. So will be eliminated. Very good, will be eliminated. This leads to a new system. This leads to a new equilibrium of the system. Always remember this. It will, if you violate, it will new equilibrium. Okay. See, this I showed you actually. Anyway, FeO-Fe curve. Along the curve, FeO coexist. Above Fe, below FeO. Percentage CO versus T plot in the last case. I have removed the figure. So those are also equilibrium state. But instead of two solid, one solid. So one less, one fewer. Here also one fewer means only one solid was there, so no solid. So this makes sense. So this leads to a new equilibrium, but the equilibrium all the same equilibrium, but degrees of freedom has increased. So like this. If F increases, what will happen? Consequence, left hand side, F is increased. C minus P, P must decrease, so that it will be, the equation will be justified. C remaining the same. So this leads to, I'll show you. This leads to a new equilibrium of the system with CO-CO2 gas mixture. With CO-CO2 gas mixture given by composition, which gas mixture? By this composition, the composition that I maintain, B prime, I maintain this. And that I maintain. When I maintain, I am forcing someone else. I am, okay, the equilibrium composition, I'm actually enforcing some composition which is actually not this two-phase equilibrium, the original equilibrium. So I am actually imposing some different composition. So I am imposing, as a result of which someone will be sacrificed. Here, easy way to understand, since it is decreasing, so reaction will move to this side, as if to compensate for that decrease, and continuous. Since I'm then you might say, sir, this way it moving, and then it will return to the previous position, to the earlier position, earlier state, earlier composition, concentration of CO. No, this again I maintain, then I will argue, I am again maintaining, then again moving, continuous, this way in successive, in successions, number of actually, you see, spells, this is continuously moving. And since I am sustaining throughout, then this removal is sustained also. This movement to the right hand side, the result is what? When I said I am maintaining percentage CO at this lower value, means CO-CO2 both are there. Lower, say 30%, means 70% CO2 all are there. Who will be then sacrificed? Who will suffer? Who will be victim? Victim is what? Carbon is, I am not replenishing the carbon. Carbon is removed. depleted. Finally, it will be extinct, will be out, eliminated. So this leads to a new equilibrium, but that is a new equilibrium. With what? Fewer phase. How many phase? Only one gas phase. B prime means only one gas phase, CO-CO2 gas. Carbon unsaturated. No carbon solid. No carbon solid. Activity of carbon less than 1. Activity of carbon less than 1 means carbon may be present with a lower activity. Means that is not solid carbon. Solid carbon has unit activity. That will manifest again, that is different issue. That will manifest in the carbon vapor like this. Okay, that is different. Okay, that is getting complicated. The activity of carbon less means physically absent. Okay, always this, so that phase is eliminated. This is removed. New equilibrium with CO-CO2 gas mixture given by composition B prime, given by composition B prime, as which I have maintained, which I have enforced B prime, third degree of freedom, B prime alone present. The new equilibrium with CO-CO2 gas mixture alone, no carbon anymore, alone present. So right, why alone? No, carbon solid, absent, because eliminated, absent. What is the gas? Carbon unsaturated gas. What is the implication of that in terms of activity? Less than 1. This is, as we expect, exceeding the degree of freedom will cause elimination of phases. This is demonstrated. This point. B automatically, third degree of freedom, there is no third degree of freedom, only 2, temperature and pressure. B automatically, dependently, but I have applied B prime as third degree, as imposing the third degree of freedom. Result is elimination of phase as expected, and we are happy. But what happens if we again exercise the third degree of freedom, not by decreasing B to B prime, but by increasing from B to, you see here it is not clearly shown here. I will show you. You follow this, very interesting. B, start with the B. This is the starting point. B automatically B to B prime I discussed B prime, B to B prime I discussed. Now I discuss B to B double prime in the form of increase, but all the same, third degree of freedom imposed, increase B double prime. What will happen? A strange thing will happen. Phase elimination, but which way? Here we found continuous this way, because CO was decreased. Now when CO is increased, it will move this way. But this way, why is the elimination? Who will be eliminated? Carbon is not there. No solid phase is this side, no solid phase is there. That is the trouble. That has caused an unusual thing. Unusual. No solid, it is moving. The carbon will be produced rather than eliminated. Produced on whatever already there. So very interesting. So then how the phase elimination take? No phase elimination. Then what will happen? But phase rule says it must be eliminated. Degrees of freedom. Then a class, vigorous class. This class, then what happens? Means it is not possible to have this gas. This is very unusual. This gas composition you never have. He can never sustain, can have. The moment you have, it will automatically drop to the state B, old, or initial state B, back. This is called unrealized, unstable gas. This gas is not realizable. It cannot produce any gas. Any gas more than this, greater than this composition, it cannot produce. The moment you make, it will shoot out. Called shooting, means carbon is produced. Shoot out, carbon will be precipitated from that. That's why I have actually given this mark, hat mark. You see, man, means this side is not possible. What I have written? Unstable gas, unrealizable gas, and also what I have written? Shooting occurs. And what is the corresponding activity of carbon is greater than 1. Have you heard of this? Activity of carbon greater than 1. 1 is pure substance as 1. So that shows impossibility. I mean, that is impracticability. So activity of carbon cannot be greater than. About carbon activity, I said along the line, along this curve ABC, activity of carbon is 1. Below, as I have showed you, unsaturated, activity of carbon less than 1. Above, activity of carbon greater than 1. As this happens, so means that gas is not realizable, is actually unstable gas, and it will shoot. Carbon will be deposited. Shooting will occur. Shooting will occur. This I am going to write as the alternative violation, but in an alternative way. This I will discuss now. So shall I give a star mark here? I should not take up. So I don't think you actually need this. This you all know. You are expert in this. Remove this. Unnecessary. Sorry. This figure is very important for 5. This is way. We are actually way behind this actually. So this is way later, this one, okay. But anyway, this is star mark. This is an interesting situation comes. But let us discuss this. What I discuss as I'm writing, this will be very helpful if it is written actually. So this. Right. This can be explained. This as if this I am again explaining further and further. I am explaining number of ways. Further and further, what I said, that you exceed the degrees of freedom, phase number of phases decrease, but same change apply. This can be explained. Still, then I will take up the alternative violation in an alternative way. First, I will show you something about this. What I discussed here, this part is actually continuing here. Continuing. This can be explained from the phase rule. F is C minus P plus 2. If F increases, we increase F, then what happens here? From this, P decreases. C is unchanged. C cannot change. Unchanged. Happy? Okay. So when F is increased from 2 to 3, increased from 2 to 3, then what happens? You see, mathematically see, 3 is C is the 2, C is the 2 minus P. Let us see what value of P you get. P is 1. So how many phases? Previously, how many phases? 2 phases. 2 phases. Now it is P is 1 because F has exceeded. So P is 1. So that is P decreases from, that is P decreases from number of phases. That is the number of phases decreases from what? Previously what? 2 phases, solid and gas, from 2 to 1. 2 to 1, decreases from 2 to 1. What is that? Only the gas phase. Only the gas phase. Only the gas phase. 1. Which phase is gas phase? Only the gas phase. Solid out. So this is P is 1, only the gas phase.
Two hours, 1 minute, 18 seconds.
5 minutes lagbe. 5 minutes lagbe.
5 minutes.
It decreases from 2 to 1. I am writing here this side. Right here. P is 1, only the gas phase means CO-CO2. CO-CO2 exits. Okay, this part. Now take up the next part, next segment of this discussion, that is, however, yes, we will violate a opposite direction. However, as I have already told you, however, interestingly, remember what I am going to do? I am violating again from B to not B prime, but B, not B to B prime. No, not this violation. I will on the opposite direction, B to B double prime, increasing the CO percentage. So now, however, interestingly, if the third degree of freedom, DOF, third degree of freedom is applied in the opposite direction, is applied in the opposite direction, that is gas composition, which is in terms of percentage CO, is increased from B, means 50%, from B to B double prime. Right, nicely, B to double prime. B to, I repeat, B to B double prime here. B to B double prime. This, there won't be, as I said, CO has increased, moving this, CO increased, so reaction will move in this direction. Equilibrium is upset, trying to re-establish the equilibrium, and in that attempt, moving in this direction, but who is eliminated here? Who is no solid phase on the left hand side. So it only produce more and more carbon on the carbon which already present. So no elimination. But how it is possible? Should be, according to it, should be one phase. That means this gas composition itself is impossible. More than this, okay, impossible. As I said already, I have said impossible, unrealizable, or what I have written here, unstable gas, and shooting will occur, okay. And the gas, what will happen? Then finally, what will happen? The gas composition will fall back on the B. There with carbon will happily stay together as before. B to B double prime. There won't be any phase elimination. Phase elimination because of unavailability of the solid phase. Solid phase. Left hand side there was solid, but right hand side no solid. So on the right hand side, of reaction 1, right hand side of reaction 1, okay. The result points towards toward the impossibility of realization of such gas composition. Comment that is
2 hours 7 minutes.
Yeah,
2 hours 8 minutes.
7 minutes.
8. 2 hours 8 minutes.
2 minutes. So that is percentage CO of such, that is percentage CO greater than B. Greater than B. Any value greater than B is impossible. It is unrealizable, or okay, unstable gas. Anything. That's why I have given this mark. H mark means above, closed, prohibited, forbidden. Okay, forbidden, above. Similarly, here also for this 10 atmosphere also similarly above, forbidden. This I have not shown. I have shown in one case, 1 atmosphere, which is typical. So greater than B. We speak of this as unstable gas composition. With what is the corresponding activity of carbon? Greater than 1. Greater than 1 is also impossible because maximum value is 1 when it is pure carbon, leading to what it lead to when it happens, activity of carbon greater than 1 is leading to sooting. into sooting carbon deposition, that is carbon deposition. Carbon deposition. And the gas, what will happen? As I told you, under this condition it is unrealizable, impossible or unstable. This gas composition will fall back on the gas composition B. For B double prime fall on the gas composition B, which is actually in this case is 50%. 50% for the temperature 948 Kelvin. So and the gas composition will fall back gas composition will fall back on the composition B. This is an interesting observation. With this we have completed example 2. Thank you very much. Okay, we will take up example 2. I am very sorry. Example 3, with this we have completed. We will take up example 4, 5, 6 next class. Thank you very much. See you for your patience and for your cooperation and attention and your interest and sincerity. Thank you very much. See you. Bye.